So, today let us revisit some examples which we have already done similar type of problems earlier, but let us do some of the problems again, so that our understanding becomes clearer. So, that is what is our topic today, that is further examples for dynamic programming. Two problems we shall be taking up in this particular exercise. One is a shortest distance problem, and the other is the longest distance or the longest path problem. The problems are very similar, but the conceptually, one where you try to find out the minimum possible path from the source to the destination, and the other one the maximum possible distance from the source to the destination. So, like the stagecoach problem that we have already discussed, let us see, we have a number of cities. To be precise, in this particular example, let us take, suppose there are 8 cities, A, that is at the first level, which may be called the source, then B, C, D at the next level, then E, F, G, and finally H, and the distances between these cities are given. If you just see that while all possible paths are available, but there is no path between D to E. So, precisely there is no path between D to E. So, you can understand that you cannot go from D to E. Now, in any dynamic programming setup, what we need to really find out, really first obtain the stages, the states and the decisions that we are going to have for such kind of problems. So, the 3 stages are essentially is the run, say precisely if you are moving by stagecoach, then the stagecoach run from the first set of cities to the second set of cities, that we can call as first stage, from the second stage of cities to the third stage of cities, that we may call the stage 2, and the third stage of cities to the destination as the stage 3. So, like A is the source. So, when you move from A to B or C or D, that is our stage 1, and B, C, D to E, F, G, that is our stage 2, and E, F, G to H, that is our stage 3. So, these are our 3 stages. The states, all the cities or nodes, that is A, B, C, D, E, F, G, H, they all represent an individual state. So, as you are moving from one set of cities to you are only moving from one city to the other, but those are the choices, the alternatives that are available. So, as you move from a city in the first level to the city at the next level, you are making a change of state. So, you make one change of state in every stage. So, since there are 3 stages, you make 3 state changes. Is it all right? But then the possible states that you can have from A, you can go to one of the 3 possible states. So, that is how the states could be defined. So, as you can see, in stage 1, you can go from A to B or C or D, and stage 2, you can go either from B to E, F, G, or C to E, F, G, or D to E, F, G, and finally from E, F, G to H. So, these are the possible states. Obviously, there could be a solution from by really having kind of a brute search or a total search kind of thing, but dynamic programming will reduce the number of iterations. That is what we are attempting here. Now, the decision variables for such a problem, that is a kind of a shortest path problem, can be defined as x n equal to where n could be 1, 2 or 3 depending on the stage, the immediate destination. Is it all right? So, supposing from A, if our immediate destination is B, then A, B is our decision variable. Is it all right? That is our destination. So, it really represents that from A we move to B. Then if E and then finally H is our next set of destinations, then final path will be A, B, E, H. So, that is what is shown here. That could be called a route. The route will be A to x1 to x2 to x3 to H. So, once again we have defined a set of stages. There are 3 stages between movement from a city to the next city. The states are the cities or the nodes, all right. So, there are 8 of them, and the decisions are the destination on every stage. So, that if we know the destinations on every stage, we can really know the route or the path. So, how do we move about? The first thing that we must have a recursive relationship. That is the essential idea of dynamic programming. So, like before, and by applying Bellman's principle, the optimum value will be a candidate which will be a value that is Fn S xn, is it not? That value which will really see the contribution for the current leg, that is the decision that you make, that is on xn, plus the optimal decision at the previous stage, that is n plus 1 if you are really going for the backward dynamic programming. So, since we are coming from back, that is why the Sn can be calculated based on Sn plus 1. So, if f star n plus 1 xn is our optimum value at the next stage, then if you add that to the current contribution of a particular destination chosen by you, that is dsxn, that will give us a given value, and the optimal value at this current stage S will be Fn star S, minimum of this xn dxn plus f star n plus 1 xn. So, that will be the recursive relationship. So, these recursive relationship we have we shall actually apply to such kind of problems, and use them to find out our minimum value. So, already we have discussed this in previous problems. So, without wasting any more time, let us move over to the stage 3 calculations. So, at the stage 3, if you look at this particular diagram, the destination is only one. So, since there is only one destination, we do not have much choice, at every situation we have to choose that particular destination, and the distances are already given, that is from E it is 11, from F it is 14, from G it is 17. So, therefore, from E these are the from E the distance is 11, and there is only one choice, that is x3 equal to H. The x3 is not going to vary, that is the decision that we make at the third stage. So, therefore, the optimum decisions will be 11, 14 or 17, and that can be really the x3 star will be H. So, it has been marked here. So, what you really got from here, that at the third stage, for reaching the destination H from S, that is let us say E, the optimal distance is 11, right. So, we already got that from E the optimal distance will be 11 if we have to reach H. So, that is what we have at the stage 3 calculations. Now, using these stage 3 calculations, by using the recursive relationship, we can really then find out the stage 2 calculations. So, let us come to stage 2 calculations. Now, here in the stage 2 calculations, we are really seeing from set of cities B, C, D to a set of cities E, F, G. Now, please look that B, C, D, this set of cities, to these are our states. The states are cities B, S, B, C, D, and the destination city which our decisions is E or F or G, and we have to see which one is the optimum, optimal distance from B, from C or from D. So, to calculate, we calculate the optimum value from E to H. Now, look here, if the distance is from E to H, the optimal value is 11, from F the optimal value was 14, and from G the optimal value was 17. So, these are our previous optimal distances which we have already obtained from our previous calculations. So, these previous calculations we will use in the recursive relationship, that is from B to E, it should be the distance between B to E plus the optimal decision from F3 star E. So, that would be 8 plus 11, because B to E is 8 and 11 is the optimal decision here. So, these 8 and 11 will give us 19. That means B to E an optimal decision will be 19. Then B to F, the B to F will be the optimal at F. What is the optimal at F? 14. And what is the distance from B to F? It is 6. So, that gives us 6 plus 14 equal to 20. Right. So, similarly, we can calculate from a given city to a destination depending on what we have. So, if you see that for B to G, the calculation is dBg plus F3 star G, which is 24. From C to E, DCE plus F3 star E, that is 18, and C to F 19, C to G 25, and D to E there is no path, right? D to E we have no path. Then D to F 21 and D to G 27. So, in order to find the optimal distances, we have to then see row wise what are our best possible paths. So, if I see from B, the best possible destination to choose is E, because calculations show here it is 19, here it is 20 and here it is 24. So, we get B to E as the optimal distance. So, B to E, E is our optimal destination and 19 is the optimal value. Similarly, from C, the optimal destination will be E again, and that particular value, the optimal distance value will be 18, because this comes out to be minimum out of 18, 19 and 25. Finally, from D, there is no path from E up to E, there is 21 value for F and 27, since 21 is minimum. So, DDF will then become 21. So, this gives us the optimal distances for our next set of calculations. So, and these paths are indicated here also, that from B the optimal distance is E, from C the the optimal distance is again E, and from D the optimal is F. Is all right. So, now we have the optimal distance from B to H, C to H and D to H, which are given at the here, that is 19, 18 and 21. These facts we can make use in our final stage, that is stage 1 calculations. In the stage 1, we are really from calculating from city A, and from city A, again we can go to one of the destinations, that is B or C or D, and if I go for up to B, then DAB plus F2 star B, and F2 star B from our previous optimal calculation we found it is 19. So, it should be A to B, the distance is 10. So, 10 plus 19 29, for C it is 12 plus 18 30, for D it is 8 plus 21 29, and then since 29 is the shortest, but it can be both for destinations B and D. So, therefore, the x1 star will be B or D, and f1 star S will be 29. So, if you look at these calculations carefully, you could see how the Bellman's principle has operated at each of the calculations. See, really speaking, although there are so many combinations of cities, all that we had done at a given stage is only seen the distances from a given city to its possible destinations. Is it all right? So, at the last stage we had seen 3 combinations, at the second stage we have seen 9 combinations, one was not available, and at the last stage we have seen another 3 combinations. So, 3 plus 9 plus 3, around 15 combinations only we have seen. And the good thing is, if we have more stages, just assume another 2-3 stages, all we have to add is, as you add more number of stages, it does not increase in an exponential manner, it actually increases in a linear manner. That is where the advantage of dynamic programming, because it is a very small 3-stage problem, the advantage is not really seen. But just assume, we have something like a 7-stage or 8-stage or even 20 stages. So, assume a set of cities with 20 different stages. All that is happening from the 3-stage, from 3-stage to 4th stage to 4th stage to 5th stage and so on. We simply add linear number of combinations, and we can still solve a 20-stage problem of shortest distance problem by dynamic programming in finite time without much difficulty. That is where the real advantage of dynamic programming comes in. Why it happens? Because once we find out the optimal path from the previous what you call stage, we can really utilize those optimal values with the current calculations. So, the current distances, real advantage really comes from there. So, what we do here, that we then combine all the optimal distances at the different stages. So, this is our stage 3, stage 2 and stage 1. So, if I really combine them all, then you see from A the optimal is B or D, from B the optimal is E, from E the optimal is H. So, it is A to B to E to H and A to D, because from D optimal is F. So, F to H. So, A to D to F to H, and the distance will be 29. So, that is how you can combine them all and really get the optimal solution for such a shortest distance problem. And here it is shown in the graph, you go from A to B, from B to E and from E to H, and the distance will be 29. And the other optimal, there are 2 optimal paths, that is A to D to F and from F to H, which will be also 29. Right. So, we earlier have seen the stagecoach problem, and now another example of similar type we have seen, where how do we really find out the shortest distance between a source city to a destination city. And I am sure that using these examples you will be able to solve all such shortest distance problem. But now let us look at the same problem once again, but from a different angle. Now instead of the shortest distance, we try to find out the longest distance or the longest path between the source city to the destination city. So, if you really have to find out the longest path from the source city to the destination city, what would really change? Will there be any change in the stages the way we have defined? Answer is no, because problem structure is the same. Will there be a change in the states? Again, there will be no change in the states. States will again become the cities. and the stages will become every run, right, could be stagecoach run or vehicle run, truck run or any such thing from a given city, I mean a set of city to the next level of cities. The destinations, I mean that is the decision variables, that will be also going to be the same. So, really speaking, therefore, if we really find out the longest path instead of the shortest path, all that we really change is the way we calculate our optimal distances. Is it all right? The change here is going to come in the way the optimality is calculated. Rest of the calculations will be very similar. Let us see then how they combine. So, first of all, as I have really said, the stages are the run from one set of cities to the next set, and there are 3 stages. The states, all the cities are nodes, that is A, B, C, D, E, F, G, H, and there are 8 states considered here. The decision variables, the decisions in the shortest path problem S will be again x n, where n equal to 1 to 3, right. So, x 1, x 2 or x 3. So, these decisions will be nothing but the destination city, the immediate destination on stage n. So, that means for A the candidates could be B, C or D. At the second stage the candidates could be E, F or G, and at the third stage the candidate could be H only, and therefore, the final route will become A to x 1 to x 2 to x 3 to H. Now, let us see the recursive relationship. Here we have made a small mistake. The mistake is like this, that this one should not be mean, it should be max. Right, because that is the change really we have, that this one should be maximizing rather than minimizing. So, we really have to maximize. So, let me write it once again, that it should not be minimizing, it should be maximizing. So, you see that mistake, if we correct, then automatically we get the longest path. So, at any point that, in fact, it highlights, this mistake highlights the change from the previous problem, that is the shortest path problem. In shortest path problem we were minimizing, in the longest distance problem or the longest path problem we are really maximizing the distances. So, but then rest of the things are all same, that f star n s will be equal to maximum of that x n, which is d s x n, the distances, the immediate distances or the contribution of x n plus f star n plus 1 x n, that is the optimal at the previous stage. Rest of the things are as we have seen earlier, right. So, the next one will be our, so if we really do the stage 3 calculations now, in the stage 3 calculations we can see that again the destination city is only one, that is only H, because from E, F, G in the last leg we can go only to H, because that is our final destination. So, here that S is E or F or G, then your H, there is one more mistake here, that is this value should be 17, right. So, this value is not yes 17, that is fine. So, this if we really look at this, then from E to F to E to H is 11, from F to H is 14 and G to H is 17. So, there is no other distances that is available. So, obviously, they must be optimal. That means, what is the longest path from E to H? It has to be 11, because there are no other paths, right. Similarly, from F to H should be 14 and G to H it should be 17. So, that really gives us the stage 3 calculations and the optimal distances, the longest distances. So, if we then move further, then we see at the stage 2 calculations, that is, the distances are to be calculated from B, C and D to E, F and G. So, by similar method the calculations are done once again. That means, see 11, 14 and 17, they were our optimal distances from E, F and G. So, we use them and use the immediate distance. So, let us say from B to E, the immediate distance is 8. So, if I add these 8 to 11, then I get 19, right. Similarly, for B to F, the dBF is 6, and if I add these 6 to the optimal distance from F to H, that is 14, we get 20. So, using them, similar kind of formula, we got all the distances from B to E, B to F and B to G, and since B to G 24 is the maximum, that should be the optimal as far as B is concerned. So, really, what is the optimal distance from B to H? It should be 24. Is it all right? So, that means the optimal, that is the maximum possible distance from B to H, has to be 24, and it is actually through G. So, therefore, look here in this diagram, if I see from B to G is 7 and G to H is 17. So, that is 24. So, by similar kind of calculations we can do for C, for D as well, and in all these cases we find that is through really happening through the point G, right. So, what we really get, that from C to H the optimal distance should be 25 and it has to be through G. That means, the immediate destination of C should be G and immediate destination of D should also be G, but the longest durations, longest distance from D to H will be 27, from C to H will be 25 and B to H is 24. So, look here, when we talk about optimal distances, these optimal distances are from that given point to the final destination, but the immediate destination is our x2 star, which are G in this particular stage. Now, using them we can combine the result in the stage 1. In the stage 1, this leg, the distances are calculated from A to B, A to C and A to D, and the immediate destinations are B, C and D. The optimal distances from B to the last, that is final destination, was 24, from C it was 25 and from D it was 27. So, those values are utilized along with the current distance, and we got 34, 37 and 35, and since 37 is the maximum, obviously the optimal distance therefore should be 37. Is it all right? So, that how we should really calculate, and this gives us, if I compare all of these, the longest path will be ACGH, that is 37, 12 plus 8 plus 17. Right. So, you see what we have done in this particular lecture, we have really given a look back into our stagecoach problem, and we have seen not only how to calculate shortest path, but also how to really calculate longest path, right. So, that is how we have done in this particular lecture. Thank you.